All right, welcome back for the third installment for today. I'm actually recording this, the final part, while I'm rendering the other video because I built a new computer and it's a beast. So hopefully nothing crashes. I could probably check my task manager. I'm sure everything is just fine. So anyway, last one we talked about on our last one we started talking about non-Euclidean geometry and spherical geometry. And some really cool things that are going on with that. So let's try to use the Pythagorean Theorem to estimate how far Christopher Columbus traveled. So you can see our globe here, which is round. He knew it was round, by the way. He started out in Spain and he landed somewhere in the Bahamas. Now, if he traveled as the crow flies, it actually would show up as a great circle circumference. Remember, cutting an orange exactly in half would be the biggest possible circumference that you could cut a sphere into, right? So if we took and cut from this point to this point, we cut through those two, the shortest distance between those 2 points would fall along a great circle circumference. And some just general ideas about that is a great circle circumference will always cross the equator twice, and it'll also cross any line of longitude twice as well, like the prime meridian. So if he kept on this course, okay, not following a course like a heading of like 40 degrees north or anything like that, but if he kept on this course, he would have crossed the equator exactly twice, right? And then he'd come around and cross it again. He also would have crossed the prime meridian twice, right? When he started and about halfway on the other side near Australia as well, right? So really, really cool stuff. And if you ever fly on an airplane for a long distance or anything like that, so like when I fly to China, we fly over Alaska and Russia, then we come back down. The reason we don't go due west and cross the Pacific and fly over Hawaii or something like that is because it's actually shorter to fly north. And the reason for that is because it's the great circle circumference, and that's always the shortest distance. So we never take a heading and follow one of these parallels. We always end up flying in a curve. So if you're in the northern hemisphere, you'll be flying up. And if you're in the southern hemisphere, you would be flying, it would look like you're curving down, but you're actually going straight. Which is really cool. So we want to estimate this distance, this curved great circle circumference distance, using the change in the latitudes from where he started and where he finished, and then also the change in the longitudes. The change in longitude from where he started to finished. And that one, again, we'll have to use an estimate at a certain parallel, just like we did on the last problem. So anyway, can we use the Pythagorean theorem when we have when we're dealing spherical geometry? So we're not on a flat surface. This is technically going to be perpendicular to each other, but the sum of these angles is going to be more than 180 degrees, right? This is a triangle. What are these angles going to add up to? More than 180. So again, this is definitely spherical geometry, non-Euclidean, and we're going to see what happens. So I've got the lat and long for where he started and where he ended up, and let's figure this stuff out. So first of all, the delta x and delta y. So the change in the latitudes here is going to be 13 degrees south. So he went 13 degrees south roughly, and then the change in longitude heading west was where most of his change went. Okay, so we've got that. All right, so this is very similar to what we did on the last one. We're just applying it to something else in this case. So here we have, we want to find the arc length, so we want to find how far south he went. So the change, he dropped 13.16 degrees from the this parallel to this parallel, right? Using the radius of the Earth, because our lines along lines of longitude, like here, they are all going to be great circle circumferences, so it's going to be the same as the radius of the Earth, okay? So we use our arc length formula. Basically, we end up with, he went south about 1,500 kilometers. Now the next part, which is how far west he went, we have to follow that along a parallel. So I picked about 2/3 the way up because that ends up working out pretty well. So about 32nd parallels where we're going to go from. So we need to find out what the radius of the circumference is at the 32nd parallel. Because remember, as we go up in lines of longitude, I guess I can actually go back to the original one if I wanted to, and I do. Here we go. Yeah, so as we go up in our lines of latitude here, our circumferences are going to be shrinking in this case. Not the case with longitude, but latitude, we do have to adjust for that. Let me go back to where it was. All right, so what is that radius? Well, again, 32 degrees is our theta. We want to know the difference between this x and the length for the radius. So we're using cosine, and we multiply by that, which gives us 5,411, just like we did in the last video. So kind of doing a little hand waving here, but I'm trying to make sure this video doesn't go super long because it went long on the last one. So, all right, degrees of longitude. Okay, so we're on the 32nd parallel. Our radius, we said, was 5,411. It's less than the great circle circumference, right? Because we're following a course instead of following along the 32nd parallel instead of going the shortest distance, which will always be a great circle circumference. I say that a lot. All right, so anyway, the difference between going from that point to that point, apparently I didn't update those. That was from China. Gives us a difference, gives us a distance west that we traveled of 6,382 kilometers. All right, so putting this together, Pythagorean theorem approximation. So he went south. I did the colors backwards. That bugs me. Sorry. He went south here, 1,465 kilometers, and he went west 6,000. You know what? I can change this. It's totally worth it because it just throws me off. There you go. Nothing is ever perfect. And I should change these too, because it matters. Thank you for bearing with me. I really appreciate it. Okay. One day it'll all be perfect. All right. So he went south, as I said, that amount, and west, that amount. These are going to be perpendicular. Lines of latitude and longitude are always going to be perpendicular to each other. So technically we should be able to do the Pythagorean theorem, right? But the problem is that this is not on a flat surface. Again, the angles, some of the interior angles of a triangle, when we're dealing with spherical geometry, is not going to be 180. It's going to be more than 180 because of the curvature of the Earth, right? So this distance here is not going to be the same. We have to use a different function, which is well beyond the scope of this course, but that's okay. All right, so if we do the Pythagorean theorem, I'm going to go ahead and actually show you that in the calculator because I can. So 1465 squared. So we'll do that squared plus 6,380 something, 82. Alrighty, and don't forget to square that. And then you got to take the square root of it, and that'll give us our distance. So boom, right there. Okay, so we want to find out what the actual value is. So what I'm going to do is I'm going to put this into, there's my China stuff from the last video. And I'm going to put in these values into the points. So the first point's where we started out in Spain. Now I'm going to have to use a negative value because we're talking about west in this case. But all right, so 37.22, which would be positive, and then negative 6.88 because it would be west. And that should be starting out. Yeah, you can see that's in Spain. And then the next one, we're not going to northern China. And so it would be 24.06 and then a negative 74.46. Okay, boom. So there's his journey, and the distance that we have is going to be 6,494 kilometers, which is really close to our estimate. So this is the actual here. And I think on this site, they might actually show you, there's a lot of good stuff here. Okay, so they show you the formula. Yeah, so this is called the haversine, or haversine, I don't even know, haversine formula. And look at all that nastiness. Doesn't that look like fun? I think it's based on the Pythagorean theorem. It's just, or using the law of sines and the law of cosines or something like that. But really cool stuff. You don't need to know all that, and they've got all the coding for the embedding and everything, which is so cool. I love this site. Lots of fun I'm going to have putting in lats and longs and getting these all this stuff out. But anyway, really cool stuff. The reason it falls apart again is because this is a curved surface. It's not a flat surface, so we can't use the Pythagorean theorem when we're dealing with a spherical geometry. So haversine formula, it works. It kind of does it for us. It wasn't that far off, but if we would have chose different points, then it'll actually get worse, because you can have some really funky things going on here. In spherical geometry, you can go a certain distance, turn a right angle, go a certain distance again, turn a right angle again, and then have another right angle, and end up where you started. So you could have a triangle, a right triangle technically, where the sum of the angles is 270 degrees. It's just, really cool stuff. I actually bought a Lenart sphere, but because of the whole pandemic thing, it might be at the school waiting for me, but we didn't get to play around with it. But spherical geometry is super cool, and I'm excited to be able to get into it even more next year. And so hope you enjoyed that. I got 2 more days worth of extensions that I'll be posting. So tomorrow we're going to do all the stuff that we would normally do outside. So that'll be indirect measurements, shadow method, mirror method, inclinometer, and how we can tell the time of the day using shadows, which is really cool. Disclaimer, it's not perfect, but last year we were able, by measuring the length of the shadow, I was able to determine the time of day knowing the sunrise and sunset within like 6 minutes of the actual time, which is really cool. So it's kind of a process that's made for summer, but I'm going to stop talking. I hope you guys are enjoying this. I'm really enjoying it. It takes a lot of time to get it all prepped, but it's totally worth it. So I do miss you guys. I love math, but I really miss all the fun things that we've done. So last call for photos and videos and stuff like that from class. I'm going to make the end of the year video. So if you'll send that my way, that would be great. So we're almost done. We've only got a few days left of school, so I'm going to stop talking now.